Okay, so this is part of what we were discussing last time, and you can think of this diagram, which intends to show the situation of scattering by an atom by considering the scattering from two little spots, little volume elements, or little points even, in the electron density distribution that surrounds the nucleus. And so what we come down to considering is the path length difference for these two parts of the X-ray beam going out to encounter the detector surface, which is way a couple of miles to the east. But you could think of this same diagram. It would equally well apply if we were considering the scattering from two separate atoms in a unit cell. I mean, in general now, what we have to build up to is being able to account for the scattering from the n atoms in the unit cell. Right? So if we just consider two atoms, it would create a situation, a diagram situation, exactly like this one. We note here that the wavelengths of X-rays that we're using are on the order of the atomic radii. Here we've got a scattering angle that is, what, I don't know, 20 or 30 degrees. You can imagine how the diagram would alter if we just went to higher and higher scattering angles. And we come down to consideration, if we're considering 2 points in an atomic electron density distribution, or two atoms in a unit cell, we consider that there will generally be a phase difference that's given by 2 pi over lambda times this difference in path lengths. K times the difference in path. This K is the one that relates to the Planck age and so on. Okay? So this is the so-called wave number, 2 pi over lambda. So what is required is a composite, for the unit cell, composite consideration of all of these kinds of effects, these interference effects. So we want to get to the situation where delta x gives us an integer number of wavelengths, and then these different pieces of the scattering would be in phase. Then we'd see a strong reflection. Otherwise, they're going to be out of phase to a greater or lesser extent, and we're either going to see a weaker reflection, or in the extreme case, no reflection, just background.
Can you explain where the 2 pi over lambda comes in there? I understand the delta x. How is that K? Where does that come from?
So that goes way back to the basic physics of waves. We talk about the wave is characterized by its wavelength and period, any wave. So the wavelength divided by the period, that's distance over time, gives the propagation velocity. And then in terms of those quantities, wavelength, period, and propagation velocity, we define these other characteristics of the wave. One of them is the wave number. The other is the wave frequency. So the wave frequency is 2 pi times omega. Now, omega has units of inverse time. And the wave number, this quantity k, is defined as 2 pi divided by lambda. So you can see how k and omega would relate to the speed of propagation.
I see.
So these are quantities that are defined for any harmonic wave, and they're just convenient ways to utilize these properties in our analysis. Okay. Let's move on. Oh, I think I have to. The computer needs its earpiece. Hearing aid, just like me. And so we've considered the same phenomenon in this kind of diagram where we're just talking about 2 points that are separated just along the direction of the incident beam, the same kind of phenomena will occur. We see these differences in the phase. So here we have this crest is falling, or let's put it this way, this crest superimposes in between maximum and minimum. Not quite at the node, but in between. That just happens to be a consequence of the way I drew the wavelength and the separation we chose. Okay, but these phase differences due to path length differences. So even if we're talking about 2 points that are on the same direction as the incident beam, there will still in general be a path length difference. If we drop a perpendicular from the one point to the ray corresponding to the other, there's this difference in path length, R1 minus R0. Okay? So this distance minus, this vector minus that vector gives us, the vector magnitude gives us this phase difference. And what we see further by considering two different points of scattering, or two different volume elements of scattering within an atomic electron density distribution, here just symbolized by a circle. We're considering scattering from the points A and B. So from A, we drop a perpendicular direction to the incident direction that passes through point B, and similarly here. So now if we start considering scattering to a higher and higher angle, what happens to these path differences? Right? We have to worry about the path difference defined by this little line segment AD, and this one defined by BC, and we keep going around and around. And what the consequence is, the larger that scattering angle, then the larger in general the differences between the wave path lengths within the atom, and the more the wave interference within the atom from these, considering the scattering from these different points or volume elements, and therefore the net result is the smaller the scattering factor. So with increasing increasing scattering angle, there is a decrease in the scattering factor. And so it ends up looking like this in a couple of simple cases. Here's scattering factor for a hydrogen atom, which at scattering angle 0 gives 1 electron. Here for carbon, at scattering angle 0 gives 6 electrons. Here for fluorine, at scattering angle 0 gives 9 electrons. And then we can consider other atoms as well. And you see that it's not simply Gaussian shapes. There are these little variations in the scattering factor curve, but it begins to look like, reasonably like half a bell-shaped curve, half a normal curve. So there we plot them in two different ways. One of them, we just normalize everything to the atomic number, so that they all, at scattering angle 0, they all collect at the point 1.0. So we consider these first few. So here's hydrogen, then here's there's 6 there. That's carbon with this little hump. Similarly for beryllium at atomic number 4. So, and then if we put them all on a basis where the vertical axis is the atomic number, the intercept of all of these scattering factor curves, and I think this includes everything up to uranium, if I remember. So we see the behavior of the scattering curves. We see that there are these interesting deviations away from just a smooth normal error curve. And we looked at it in terms of a polar plot too. So here it's pretty clear in this diagram with the sodium ion, a 10 electron sodium ion, as we go to, so here's scattering angle 0, here's about maybe 20 degrees, here's minus 20 degrees, and so on going around. But as we go to higher scattering angles, these scattering, the length of these scattering factor vectors are getting shorter, and finally the shortest is for the backscatter, which we can't measure anyhow. And then we dissected the scattering. We said we could dissect the scattering factor curves according to the electron configuration of the atom. And in this case, we looked at a simple case, the scattering by the carbon atom. So its electron configuration is 1s2, 2s2, 2p2. So altogether 6 electrons. Those 1s electrons are the ones that are closest to the nucleus on average, and the valence shell electrons, the 2s2 and 2p2 subshells, are where the chemistry takes place between the carbon atom and whatever other atom it's interacting with. The core electron stays pretty fixed. And those core electrons are the ones that are moving fastest, they have the highest kinetic energy, and the shortest, on average, orbital radius. So just some rough calculations here. When we do this plotting against sine theta over lambda, we don't actually have to measure the scattering angle. It's going to vary with wavelength, but if we do this ratio, then we've got essentially a normalized variable. So if we consider the situation for a minimum d-spacing of 1 angstrom, now this for protein crystallographers is a very high resolution. 1 angstrom is great if you can get it, and you seldom can. But that would correspond to our d-min sine theta over lambda out here at 0.5. And notice that the valence scattering from a carbon atom has essentially disappeared by then. It's fallen to 0. It's actually gone a little bit negative, and then it comes back again. There is an oscillation in this scattering factor function. But that scattering from those electrons close to the nucleus, it persists. It doesn't fall off to 0 nearly as fast as the core electrons. The valence shell falls off much more rapidly than the core. And this is a pattern that holds true for other atoms as well. We might have a core that can say, for example, we have a diagram coming up of a potassium ion. The core might be both K and L shell electrons. 1s2, 2s2, 2p6, right? And then there'd be whatever the appropriate number of valence electrons. Why don't we go to that? So yes, this is a plot from an absolutely classic book on the physics of X-ray diffraction. So what James, by the way, is a physicist who went on the Antarctic expedition, not the one where they perished, and I keep mixing up the names of the leaders of the two expeditions, but he was on board, probably writing his book on the optical principles of the diffraction of X-ray. He was a professor in South Africa. I forgot which of the South African universities. But what he plotted here was the radial variation of the electron densities for each of the orbitals, or subshells really, that he's considering for a potassium ion, which is isoelectronic with a noble gas argon. So you can see there is certainly structure to these things, and the higher we go in principal quantum number, the more structure there will be. There are these nodal points where the density falls to 0. And to get the scattering factor that corresponds to this configuration of electron density, so here we're in crystal space or direct space, we have to Fourier transform each of these guys to get their corresponding scattering factor values in reciprocal space. So for the 1s electrons that peak very close to the nucleus, it falls to 0 at the nucleus, and that's because of the appearance of this R square out in front of the radial function. That's a consequence of doing a three-dimensional spherical averaging of the atomic electron density distribution. But very close to the nucleus, it's maximum. At well under a tenth of an angstrom. But that one that's very near the nucleus gives this scattering factor curve that hardly falls off over the range we're considering here. Okay? And if we look then at these 3s and 3p orbital electron densities, we see that they fall off quite quickly, and in fact go negative and then come back again. So the net effect is given for the atom. We have to sum up each of these electron densities point by point. So this maximum would get pushed way up above because there are these other contributions underneath it. And to get the net scattering factor for the potassium ion with argon electron configuration, we have to sum up these scattering factor components for the various electronic subshells. So here it is. We only consider it out to quite a modest radius in reciprocal space just to get the principle illustrated. But at 0 scattering angle, at sine theta over lambda of 0, we've got the 18 electrons. Oh, here's the Technicolor version. Okay, same slide with color. So now if we consider, just now for the moment, the radial electron density distributions. So here we had it shell by shell. We have the 1s electrons, the 2s electrons, 2p, 3s, 3p, and so on. And the next would be 4s if we keep going to larger atoms, and then the 3d shells, and so on. So there is this shell structure to the atomic electron density distribution. And when we just add up all of these components to get the total radial electron density distribution, well, of course, again, the peak corresponds to the first principal quantum level, 1s2, but then for the 2s and 2p electrons, we get a subsidiary peak. For the 3s and 3p electrons, a smaller subsidiary peak, but you can see these diagrams that you see in the basic, I should have tried to copy one, I guess, in the basic chemistry textbook that are illustrating the shell structure of atoms. You have these annuli of high electron density, and then in between annuli of very low electron density. There are, in fact, nodal spheres where the electron density for an atom fixed in space falls to 0. And so what about this business of the scattering factor going negative? Now, the electron density doesn't go negative. It can fall to 0, but it can't be negative. Electron density is a non-negative quantity. Well, here are two functions that exhibit the kind of behavior that the scattering factor curves corresponding to the electron density. And in fact, for our purposes, it's this one, the function b, all right, which is the function of the form sine x over x. So at x, here is the horizontal line, at x equals 0, this function goes to 1. And that maybe you find that puzzling because when we go to 0, 1 over x goes to infinity. But the way you get at the value of this function at x equals 0 is to first differentiate the numerator and denominator. and then evaluate that ratio, the derivative of sine x divided by the derivative of x. Well, the derivative of x is 1, okay? And the derivative of sine x is the negative of the cosine. So now you can see where negative values, that this function can have excursions to negative values. This is also an interesting function, which is important, becomes important in biological crystallography. It's part of the functional basis for molecular replacement solutions to the phase problem. And I think weeks from now, we'll have a look at that and see where this other useful function enters the picture. And this is where they all come from. This is spherical Bessel functions. The zero-order one is sine x over x, and then you get more intricate functions, but you see how they have this family of oscillatory behavior. Notice that for J0, the sine x over x function, what is that intercept on the x-axis? It's pi. And so the first crossing for the zero-order function is at pi. Right? That was just an attempt to get a larger scale diagram. So these items of information that are needed as numerical values to calculate structure factors, either by hand or in computer, the scattering factors have been tabulated at small intervals in sine theta over lambda. Here these intervals are changing by 0.01 in sine theta over lambda. And for a selection of atoms, the hydrogen atom, free atom, or zero valence atom, and the hydride ion with its 2 electrons, okay? The helium atom with its 2 electrons, lithium plus, beryllium 2 plus, and so on. So for all of the elements and their common monatomic ions, this table of data exists, and the way that it is usually, and you can see this tabulation if you pick up the international tables and just browse in volume 4. That's the old international tables. In the new international tables, you'll find this kind of a tabulation of the scattering factors, where for each of those columns of numbers in the previous slide was fitted by 4-term function like this, a sum of 4 terms in which we've got a coefficient A, a coefficient B, and a constant C. So you can fit the variation, all those scattering angle curves that were on the composite diagram where they, in some places, smush together. A function of this form fits it very well. So what's tabulated here are the least squared evaluated coefficients for a function like this. So we don't have to just be considering steps of sine theta over lambda, say of 0.01, 0.02, 0.03. Here we can calculate at 0.015, for example, or 0.0223 in this function. So we can calculate the scattering factor value at any desired sine theta over lambda value. Now, where do those numbers come from originally? Well, one of the big hurdles in the early days of diffraction physics was to actually measure scattering factor values, not in that fine interval, but to confirm the theory. The theory predicted certain values, and you want to make the measurements to confirm that. In fact, the predictions were correct and were confirmed. Why did I start to tell you that? Oh, well, it was just nice. And some of the behavior, so where do they come from? They come from quantum chemical calculations. There are 2 or 3 different approaches. The most modern one is giving the most reliable value, where they try to account for what makes a quantum chemical calculation sophisticated is to account for electron correlation. It's not just a matter of nucleus electron attraction and electron-electron repulsion, but electron A and electron B behave in a correlated way, and that's a much more complicated computational, theoretical and computational text. But here was what happens with ionization. If we consider the aluminum atom and its triply positive ion, okay, so aluminum gets happy with an inert gas or a rare gas electron configuration, this one, the argon, not the argon, neon configuration, by giving away 3 electrons to some other atom that would like to have them. So it becomes a 10 electron ion. And oxygen, the oxygen atom here, with atomic number 8, likes to have 2 additional electrons to achieve this neon electron configuration. So what happens is when you give away electrons, the scattering factor falls from 13 to 10 in this case. When you gain electrons, the scattering factor value increases, in this case from 8 to 10. So it then becomes a question for biological crystallographers if you've got situations where you have, say, magnesium ions, or even in more case, some other soaked-in heavy atom or whatever, you have available the scattering factors from those 4 term sums for the ionic configuration as well. I think the usual practice at the resolution that protein crystals provide for us in the diffraction experiment, the only neutral atoms are considered. So to worry about these kinds of differences in hundreds of amino acids molecule is really varnishing the scaffold work. But for material scientists, for bioorganic chemists, for inorganic chemists, these differences matter, and the calculations have been done to take them into account. And it's interesting to keep in mind what's happening electronically as the atoms do chemistry together. Here's an interesting case. So when I prepared these slides, I was talking to a material scientist, not a biological crystallographer. So I pulled them out on all the presentation. But the aluminum ion with charge +3 is isoelectronic with the silicon ion with a charge +4. That is, they've got this argon configuration. Is that argon or neon? Oh, it is argon. Okay. No, that's a mistake. That's neon. In any event, the curves for these 2 isoelectronic atoms are very similar. So they both are 10 electron instances, so they've got that point in common. And as you follow out their scattering factor curves, their computation or the calculated scattering factor, just this very little difference between aluminum ions and silicon ions. So that means that X-ray scattering is not an easy way to distinguish between aluminum and silicon. So in aluminosilicate crystals, which are practically very important, zeolites and so on, the problem of deciding which of these guys surrounded by oxygens are aluminum and which are silicon is challenging. So other techniques are used to make that determination. Okay, so now we want to consider the modification of the atomic scattering factor due to the fact that atoms are never at rest. They're always undergoing thermal agitation, even at the absolute 0 of temperature, because the quantum chemical treatment of the harmonic oscillator, it doesn't, the first quantum shell is slightly above 0. The first quantum level is slightly above 0. So there's the so-called 0-point energy for a harmonic oscillator. That applies to all of the atoms that are jiggling about their mean positions in crystals as well. So the structure factor is this sum over all the atoms of the unit cell, each atom with its own atomic scattering factor. Now that scattering factor modified by this function, here symbolized D to honor Peter Debye, who was a Dutch physicist. Waller was, I've forgotten, Swedish or Norwegian. But they both worked on the same problem, so their names are, but we use D for Debye. And then multiplied by the exponential 2 pi I h dot x plus k dot y plus L dot z, where the x, y, and z are the coordinates of the atom A, each in, so there's a position vector for each atom A, which has x, y, z components. Here we're using the convenience of vector notation. And we put these angle brackets around that position symbol to say that we're here concerned with, in calculating the structure factor, we're here concerned with the mean position. The atom's jiggling around, but it's jiggling around some equilibrium mean position. So this Debye-Waller factor, what is it? We know that the atomic scattering factor is the Fourier inverse of the atomic electron density distribution. We just spent a lot of time talking about that this morning, and we had talked about it the other day too. So the atomic scattering factor, it has at most a value of the atomic number of atom A, and in principle it could fall all the way to 0 if we could measure out to high enough resolution. It will get very small at high resolution. The Debye-Waller factor is also a Fourier inverse of a probability density distribution. What is the distribution of? It's a distribution of these quantities U sub A, where U at any instant is the value of the difference between the position of the electron at that instant and the mean position. Okay? So it's a displacement parameter, a thermal displacement parameter due to the thermal agitation of the atom. Okay, then these two enter as a product here, F and D. So the product of these two Fourier transforms, Fourier inverses, remember we said that if we have a convolution product of these two kinds of functions, the electron density function and the probability distribution function, this is a probability distribution function 2, but anyhow, the convolution product of those two functions, Fourier transform of that product, is equal to the product of the Fourier transform. So we have a Fourier transform that gives us this factor D, another one that gives us this factor F, and the product of the two is given by the Fourier transform of this convolution product. And a convolution product is a formal way of allowing for the influence of the one function on the other, how the one distribution modifies the other and vice versa. So a probability density can be at most unity, so that is, the U's must, even at U equals 0, right, 0 displacement, then the probability density function would have a value of unity, and they fall off also with, they can fall off also. So as we go to higher resolution, both the F and the D factors in the structure factor expression are declined. So to elaborate then, what is this D factor? It has to do with the product of the displacement and the reciprocal lattice vector for the reflection that we're considering. Okay? So this D value is going to change from reflection to reflection because there's this directional dependence. Okay? And the physics is such that it works out that there's a prefactor of 2 pi squared. No i's in this. This is a real valued function with real valued exponent variable. And the way this gets evaluated, we can say, okay, we're to get this dot product, we multiply the U value by the length by the unit vector in the h direction, and then multiplied by the square of blah, 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 blah. So basically it comes down to a quantity that is dependent on the mean square displacement of the atoms, each atom. That would be a sum over these, right? This is a term in sum, one for each atom, divided by the square of the d space, where we've got the length of the reciprocal lattice vector. Remember, it's 1 over the interplanar spacing, which is twice sine theta over lambda. Another way to think about it is that this mean square displacement, what we're concerned with is the projection of this mean square displacement of the atom onto the direction of the reciprocal lattice vector. That is, onto the direction perpendicular to the scattering planes. Right? Remember, H is perpendicular to the family of planes with indices H, K, L, or H. So the most common way that the Debye-Waller factor appears in protein structure factor calculations is this one. So we just approximate it by a coefficient b, always referred to as a b factor. But what we need to keep in mind, that what b really is a factor representing the mean square displacement of the atom about its mean position. So now we can have some illustrations of that kind of thing. So what the implication here is, when we just reduce things to a single coefficient, a single b factor, a single mean square displacement factor, we're assuming that the vibrational excursions of the atom about its mean position are equally probable in all directions. That's a simplifying assumption. As we shall see when we look more closely, that's an approximation. But here's the effect of the B factor. Let's consider on, say, a carbon atom. So if B is 0, this is the parent scattering factor curve for a carbon atom, a value of 6 at 0 sine theta over lambda. If we apply a B factor that has a magnitude of 10, what it does is it increases the steepness of the fall off. It contracts the scattering factor. But what does a contraction of the scattering factor mean? Contraction in reciprocal space means an expansion in real space. So these B factors correspond to a smearing of the atomic electron density about the mean position. And if we do more smearing, then go to a B value of 20, then an even steeper fall off in the carbon scatter. Right? So as the thermal vibration or disorder, which is in biocrystallography is very often the main actor, the smearing by whatever mechanism, by thermal agitation, or because there's a disordered side chain that has maybe 2 possible probable conformations and so on, the atom out at the end of the side chain is smeared around. And therefore, the scattering from it is weaker, and therefore it's more difficult for us to find in electron density maps. Well, more difficult for you to find. I don't look at so many electron density maps anymore. Just for meditation purposes. So, okay, the scattering factor for the carbon atom is equal to its at-rest value multiplied by this exponential Debye-Waller factor. So, people refer to Debye-Waller factors and use that Debye-Waller factor terminology as synonymous with B factor. Well, that's not quite true. The Debye-Waller factor is an exponential function. So this whole thing, exponential minus b sine theta over lambda to the quantity squared, that's the Debye-Waller factor. The B factor is the coefficient that's related to the mean square displacement of the atom. So what are those mean square displacements for these simple cases that we looked at? So for the 2 cases of 10 and 20, the mean square atomic displacement of that carbon atom is 0.13 square angstroms, 0.25 square angstroms. That's the mean square value of the atomic displacement. The root mean square value is 0.36 for B equal 10 and 0.5 angstroms. So we go from square angstroms to angstroms to the first power with this square root technique. And so you consider now a B factor of 20, which is kind of modest for atoms in protein molecules. It can easily exceed that. Average B factors over the molecule might be 30, even in a case like, say, insulin crystals, that I do have some experience with, that scatter to quite high angles. Well, we at the synchrotron, we collected 1 angstrom data for insulin crystal, zinc insulin hexamer. So the way you can, in your head, easily convert from mean squared displacement to B factor, or the other way around, very often what you see for the structure you're looking up is a tabulation of the B factors, but what's really physically important is what is the root mean square displacement of the atom that has that B factor. Well, you multiply by 8 pi squared. Oh, that was on the previous slide. Wasn't it? Yeah. So the physics is such that what B means is 8 pi square, because these pi square enter in here if you follow through the logic of the derivation. B is 8 pi squared times the mean square displacement. So you consider that for B of 20, you get 0.25. This is a pretty good approximation. I think it's 79.8 or 79.9 is a free significant figure value. So you can get some feeling for how much an atom is moving in a structure by doing this kind of mental calculation. Multiply B by 80. And so think of this. Here's at the modest B factor of about 20, modest in biological crystallography. The root mean square displacement of that atom is half an angstrom. Well, a carbon-carbon bond length is 1.5 angstroms. Carbon-oxygen bond length is 1.2 angstroms. So we're talking about a significant displacement of the atom, and 20, as I said, is a modest number. Values like 60 are not uncommon, as we'll see in some illustrations. For example. So here's a situation where the diffraction data was to good resolution, say maybe 1.2 or 1.3 angstroms. I didn't go back to the original paper to look that up. But here's the results of doing the crystal structure modeling against the experimental data using individual atom B values. Okay? And the color coding is like through the spectrum. So the atoms with the smaller B values are going to be at the blue, violet end. The atoms with the larger B values are going to be at the red end. So this is the isotropic modeling. So it's averaged over all. It's assumed to be equal in all directions. But it's not equal from atom to atom going out the chain. If you've got decent resolution data, you can say, okay, this atom out here ought to be pretty much like the C alpha atom, or this C beta atom hiding here ought to be not much greater than this guy. And going out the chain, we allow the B values to get larger. So they're restrained. They can only depart by a certain amount, certain uncertainty, from their neighboring atom. This is one of the ways we can control an electron, a refinement, and not have this side chain just wandering off. So here are these two guys. I don't know maybe they're in the same chain of density, but here's a more extreme case where this oxygen atom or this atom out at the end, or this could be a methyl group. And remember, it's not red as oxygen and blue as nitrogen. It's red is a lot of vibration, a lot of motion, and blue is much less, and green and so on, intermediate. So that's assuming that each atom has its own B value, but with the restraint that the B value for a given atom can't be all that much different from that of its bonded neighbors. But now if we allow for the 6-parameter model, in order to allow for different motions in the 3 local directions, x, y, z, for about each atomic nucleus, it takes 6 parameters, not 1 B value, or not 1 mean square displacement, but a total of 6, 3 orthogonal components, and then 3 that are giving the correlations between the two, any two directions. So here we go again, we're at blue, the displacements are small, and generally the smaller the displacements, the more nearly isotropic they look. Okay? So when you're close to the main chain or on the main chain, if you've got, if it's an ordered chain, then these little blue, almost spherical atoms, and then as you go out a side chain, this might be what? I don't know. It could be an arginine or something like that. I don't know. But as you go out the side chain, these guys are growing. But in the same way, we impose the restraint that the difference along a bond direction between 2 atoms must be quite small, right? Because you can't, the bond stretching is high frequency and low amplitude. So in the direction of the chemical bond, the mean square displacement should be, the difference in mean square displacement should be very small. But there could be sizable differences between the displacements in the directions perpendicular to the chemical bond. Here, so this ellipsoid gets modeled by, because of the different axial directions. If we make an isotropic approximation, it gets to be this. Why are these guys looking ellipsoidal, even though we said that we're using the isotropic model? Well, the farther out a side chain you go, the more freedom of motion, the more degrees of freedom for the vibrational motion there will be. So, and then when you apply that atom-to-atom bond constraint that they can't differ much, then the net result is in this isotropic model, because of the overall motion of this side chain, these atoms end up looking ellipsoid. But here it's a 6-parameter fit to capture the anisotropy of the motions. The Phoenix website is very good on their description of how you get this information out of the Phoenix refinement. Affanine is a real gentleman, a Russian gentleman. He answers his emails and everything. And he'll even take your data and help you out when you're in a position where you've got disorder problems and you can't quite model it with disordered side chains or 6-parameter mean square displacement factors. So here's the same kind of thing, but depicted with respect to the mutually perpendicular directions that define the ellipsoid for each atom. So there's some transparency in these ellipsoids. So here we have a tyrosine residue, okay, NCCO. So we have a peptide link that's not quite planar, actually rather sparse. Okay, so C alpha, C beta, C gamma, then the where C delta. Oh, okay, then this is where it splits. This is the 6-membered ring. First atom in the 6-membered ring is C gamma. So we got delta 1 and delta 2, epsilon 1 and epsilon 2. Okay, now we come to the zeta carbon atom and the eta oxygen atom, just going out that tyrosine side chain. And here's we may even conclude on this. Oh, I had a couple other things I wanted to talk to you about. But anyhow, here's an interesting example. One of the co-authors of this paper is the guy whose name just went away, Randy Reed's colleague. It'll come to me in a minute when I stop thinking about it. But he and his colleagues, he's very strong on this guy I'm referring to, very strong on computational matters, and he's really gotten into molecular dynamics simulations in a big way. So he's learned off. Done a lot of collaboration with Martin Karplus, for example, at Harvard, and the other people. These are people who do things like win recent Nobel Prizes. So what he did is he did this molecular dynamics simulation for this. This is a 35 angstrom domain of a protein that I hadn't heard of before until I looked this up, called villain, which is a cytoskeletal protein, a multi-domain cytoskeletal protein. And there is this so-called headpiece domain, 35 angstroms long, and its secondary structure involves 3 different helices. The helices are not evident in these guys. So what he did was he did the molecular dynamics simulation for I don't remember how long a time period. So you get at each kind of click along the dynamics pathway, you've got a structure. So we take, I think they took the best 100 structures, the 100 lowest energy structures, and averaged them. And then from that average structure, computed made-up structure factors. So they calculated so-called observed structure factors from the molecular dynamics model. And then what about, and so this is a difference electron density, okay, positive and negative density. So the modeling is not good in these areas. So that's how they got the FOs. So they're really theoretical FOBs. They're not actually observed. They are calculated too, but from this molecular dynamics simulation, because you can calculate the structure factors from the molecular dynamics simulation. If you know the atomic positions, and you know their mean squared displacements, and you know their scattering factors, you can calculate the FOBs. And furthermore, they did the calculation in such a way that they had lots and lots of water molecules simulated, not in specific positions, but in the way that these molecular dynamics people do things. Okay, so they get those set of structure factors, and then they take this model as a search model for molecular replacement. So they start with this end model, they do the molecular replacement, they get a solution, they refine it in the same way that you guys would be refining your crystal structure once you've got, say, a molecular replacement solution, a heavy atom solution, whatever it might be. And at the end of the refinement, they plot this difference density map between the simulated FOBs and the calculated F-calcs. Big trouble here. So the crystallographic treatment of the average of the molecular dynamics models underestimates the motion in this neighborhood of the molecule. Things are really actively moving here. So these are the ellipsoids that come from the averaging of the molecular dynamics models. So this is the kind of thing that NMR spectroscopists see, a lot of smearing and agitation. So it's also considerable here in the places where these. So it's a very interesting study that, it's almost there, the name, was done. I can send you the paper, it's a fascinating paper, especially if you're interested in how good are dynamics calculations compared with experimental crystallographic analysis. There's a way to go in improving both the simulations, because they can't run them long enough. You know, they're computational expensive running those simulation calculations if you do it for tiny time steps out to, nobody gets to a millisecond. So there could be a lot of other difference due to termination of the course of the simulation. And they've got restraints in simulations too. I mean, it's not just that every atom is a free actor. That's not the case. Okay, so here, to bring it back to Roop's book, so, I mean, he doesn't talk so much about the last couple topics, the anisotropy of the atomic motion in proteins and crystals, but he does remind us of the important result, really, for much of what we've been talking about over weeks. We can calculate for each reflection, H, a structure factor, and the components of that structure factor although we haven't explicitly stated it, we've been just assuming that the structures we're talking about are orderly, but there could be a fractional occupation number, something less than 1, greater than 0 and less than 1. If, for example, there are 2 different conformations for the atom J, or 3, then the n value might be 0.5 or 0.3 or something like that. Then there's the atomic scattering factor for that atom labeled J, and it depends on scattering angle, sine theta over lambda. There is this Debye-Waller factor for atom J. It's got its own mean square displacement parameter. Okay. And then there is the exponential kernel for Fourier transforming from electron densities to structure factors. E to the 2 pi I h dot x. X represents here a vector, x, y, z. H represents HKL. So I went and looked for this exercise on page 627. I don't know, can't find what the hell he's talking about. I'm going to have to write the burnout. Maybe this, I tried 267 and I didn't try 762 or, the other possibilities. So he wants you to consider this equation and put in, say, the case n equal 1, f equal 1, and b equals 0. Then what happens? Well, if we put in b equals 0, then this whole thing here, the exponential quantity, goes to unity. E to the 0 is 1. If we put in a unit scattering factor, say the same scattering power as a hydrogen atom, okay, that's 1. Okay. And if we, what was the other part? And say n equal 1. So this whole, if we say that this site is fully occupied, this structure factor for reflection H just comes down to e to the 2 pi I h dot x. And in practice, he points out, he had gone through the symmetry transformations back in, I don't know, chapter 4 or something like that. Maybe 5. But we don't have to sum over, in principle, we can always sum over all the atoms of the unit cell. That would give us the total structure factor for the unit cell. Okay? But we don't have to do all that summing. We can economize on the work if we just sum over the atoms that are in the independent asymmetric crystal chemical units. So we don't need a whole unit cell if other molecules in the unit cell are generated by symmetry operations. So if we're not in space group P1, where this would apply, if we have even just a twofold axis, then we could just calculate for one molecule and then sum over the symmetry to get to the other one. Okay? So if the symmetry were along the B direction in a monoclinic case, say P2, then we have for every atom at XYZ, or every molecule at XYZ, we would have another one at minus X minus Y, Z, for a twofold axis. If it's 2 sub 1 axis, we'd have one, the second one would be at minus X. What did I say? No, if the twofold is along the B direction, we would have minus X, Y, minus, right, for the twofold operation. And then If it's the 2 sub 1, then we add a half on along the B direction. And for higher symmetry cases, this expression gets looking more complicated, but it means for a much more computational economy, especially important when, in the old days when people were doing this by hand. So these quantities O represent matrices that transform from H into X, Y, Z, and vice versa, and so on. So in practice, this is what's done, but in principle, it amounts to doing this. And so what he indicates here is how structure factors from summing over the different atoms of the unit cell. So we have, where did we start? F1. So for the first atom in the unit cell, we get this structure factor, then another one that adds vectorially. So each of these guys has their own amplitude and phase. We go around. And so the net result is for the reflection F sub H, it's got these 7 components, we're say summing over 7 atoms in the asymmetric unit or in the unit cell. We end up with this green vector for that particular structure, that particular value of H. The different orientations of these F components are due to the different scattering from the 7 different atoms. So we have a vertical part, a B component. The IB component is here. The magnitude of F times the sine of the phase. Over here we have the A part, which is the magnitude of F, the cosine. And the phase itself is given by the arctangent, the overhead. We've gone through that several times, but diagrammatically here. And then he gives a couple of, just a smattering of examples. There's this BPTI protein, which is everybody's exercise protein for phasing, testing, and all kinds of various things. But it's a P2 sub 1, 2 sub 1, 2 sub 1 space group. And that means that special reflections, like the axial ones, this 200 reflection, or the zonal ones, like of the type 101, 201. So everything with the K index of 0, for example, these guys have the loop highlighted in green. They have either 0 or pi phase, either 0 or pi. The ones that are highlighted in yellow are what are called systematically absent reflections. This is something I'm pretty sure Eddie will go over with you guys, or sometime, that he will go over with you guys. So that symmetry that's due to, say, 2 sub 1 axis or 3 sub 2 axis or whatever, that imposes on the phases conditions such that the magnitude goes to 0. So these are missing reflections. If we're going out to 100 along the x-axis, along the h-axis, so here's 100 and its opposite reflection, we don't find a magnitude for that 100 reflection, although we do find a good magnitude, a good intensity for the 200, but then we miss the 001 and so on. Okay? There are conditions that cause the magnitudes for these classes of reflections with odd K or L to vanish, and so on. So this is the beginning of the table, 7,200, 7,300 more to get to the end of the list of the structure factors for this small protein. Bovine, pancreatic, trypsin, Panu. Okay, the author was Panu. Panu and Reed are the guys who really got the ball rolling on maximum likelihood refinement of crystal structures there very early on. We'll talk in some weeks about their contribution and what has followed. Okay, so this is another one, a slide to bring us back to Wood's book. It's one of his slides. So he said, oops, the intensity for reflection H depends on the intensity of the beam we're hitting with. Okay, so the scattered intensity will depend on the incident intensity. Intensity, by the way, is a quantity in physics which has dimensions of energy per unit area per unit time. So it's like power per unit area. Okay, so, and this is a bunch of constants. We'll see in a minute what they look like. This is the so-called Lorentz factor. This is something else I think that we'll be discussing with Eddie. If not, we'll talk about it at some future time. This is a polarization factor. That we've already talked about, the effect of the polarization of the scattered beam, even if the incident beam is unpolarized. And then here's the square of the structure factor, F star F. So if we elaborate that notation a bit, which is what I started to do, and then somehow math type killed me, I had more to do here. So the integrated intensity that we measure is equal to the scattered intensity. We're rotating the crystal in order to get the reciprocal lattice point through the A-walled sphere. So there's a rotational speed, velocity. So we have energy times inverse time, energy per unit time, and then we divide that by energy per unit area per unit time. Interestingly, the physical dimensions of the intensities, the integrated intensities, are area. There you go. It's just the way things work. But these we're kind of familiar with already. Here's the Thomson scattering for a single electron. Here is the cube of the wavelength. Here is the ratio of the crystal volume. How big a crystal are we scattering from? And we're assuming, for simplicity, that the crystal is of a size such that it is bathed in a uniform incident beam. So it's smaller than the diameter of the incident beam. That's a simplifying assumption that it isn't a required assumption. It can allow for crystals that stick out of the beam and so on. The crystal volume divided by the unit cell volume, that quantity squared, this absorption factor. So for each element, there is an absorption coefficient, and the longer the path of the beam through the crystal, then that coefficient multiplies the path length, coming in and going out. T0 for the incident beam, T1 for the scattered beam. Right? And these are quantities that are also tabulated. We know their values for all the atoms. And then we have to sum over all points in the crystal. That's the tricky part. So what we end up doing is subdividing the crystal in our imagination or in our computer into tiny little blocks, and then do an actual summation rather than an actual integration. Each little block would have a particular volume. This is the Lorentz factor. It has to do with how long does it take the reciprocal lattice point to pass through the A-walled sphere. Now, the A-walled sphere, we can imagine, and we will go into this later on, the A-walled sphere has a certain thickness. It's not just an ideal Euclidean sphere. It has a certain thickness. Why? Because there's a range of wavelengths in the incident, a narrow range, but it's not strictly monochromatic radiation. Why else would it take time for the crystal to pass through the A-walled sphere? Because the reciprocal lattice point also has a volume, in a sense that surrounding the peak of the intensity in the scattered beam, there is some background and so on. So we don't have a reciprocal lattice point, we have a reciprocal lattice volume, little tiny volume. So because of the volume of the reciprocal lattice point and the thickness of the A-walled sphere, there is this factor, which in the simplest case, is just 1 over the sine of the scattering angle. In other geometries, more trigonometric functions enter, but it's all just dependent on scattering angle. And then here's the polarization factor that J.J. Thomson worked out long ago. And here's our square structure factor. amplitude, the product of our structure factor and its complex conjugate. So I'll complete the rest of the story on this slide. The point is we know how to calculate the structure factor. It's the sum over the atoms of the occupancy factor times the atomic scattering factor times the Debye-Waller factor times the exponential 2 pi I h dot r or dot x. Okay, so we can know what those structure factors mean. Here's how they get represented in the intensity. The intensity that we measure is proportional to the square of the structure factor magnitude, but then adjusted. These guys are all simply geometrical factors. These guys are constants of the experiment. We're assuming one wavelength. We of course assume one charge on electron mass and so on and so on, and one volume for the crystal and one volume for the unit cell. So this is a lump of constants for the experiment: K, absorption factor, Lorentz factor, polarization. Okay, so this is a good time to stop, even on time.